This is the third video supplement for CIS 343, Grand Valley State University's Programming Languages course. This video discusses name-value bindings in Scheme. At least that's the main purpose of the video, but I also spend quite a bit of time on debugging. Specifically, I give you some pointers for detecting and adding missing parentheses, and I also give you some pointers for interpreting the often cryptic error messages produced by the Scheme runtime system. In the last video, we wrote a simple function to convert Celsius to Fahrenheit. This function only had one line of code, so this time let's write something a little more interesting. Let's write a function that uses the quadratic formula to calculate the roots of a quadratic equation. And rather than using the interactive Kava shell, this time I'm going to write my Scheme code in a separate file. So, following the steps I outlined in the previous video, I'm going to make a directory named quadratic, then open that directory in VS Code, and create a file named quadratic.scm. So I'm going to give that file a name by just saving this untitled file. Now, although some of you may have this permanently burned into your brain, like a cattle brand, I'll put a copy of the formula up here on the screen. Negative b plus or minus the square root of b squared minus 4ac all over 2a. I hope hearing me rattle that off brings back more good memories than bad. Apologies if it doesn't. Okay, before I get started, let me bump up the font size a little bit, make it a little easier to see on the video. All right, so let me start by creating the stub for the function. As you should anytime you write code, every function should have at least a brief comment at the beginning. Remember, comments start with a semicolon. Then I'll create a set of empty parens. Creating parens in pairs helps avoid losing track of parens, which is very easy to do in Scheme or any other Lisp dialect. And this is going to be a define. We're defining a function, and then the function name, and the parameters a, b, and c. These are, of course, the coefficients to the quadratic equation. And then we've got room in the middle there for our lines of code. This certainly isn't a required process, but I find that it helps me keep my code neat and organized. And perhaps most importantly, it helps me avoid creating mismatched parens. Now notice two things here. First, if we implement this formula the same way we implemented Celsius to Fahrenheit, the code would be nested so deeply it would be hard to follow. Not impossible to follow, but more difficult than it needs to be. So we should apply the golden rule here. Imagine you were to walk into a company on your first day and be asked to debug or update this code. How would you want it written? Also, as we're writing this function, we're going to be calculating two different values, the two different roots, the plus minus part. So you're going to need to use the expression that calculates the discriminant, the square root part, two different times, one for the plus and one for the minus. Entering that code twice, or cutting and pasting it, would violate the don't repeat yourself principle of good programming. In traditional programming languages like Java, C, Python, and so on, the solution is to store this discriminant value in a variable so it can be used multiple times. However, pure functional programming languages avoid variables. Well, more specifically, they avoid mutable variables. They do, however, allow you to bind values permanently to names. This is kind of like creating constants in C or Java or whatnot. So to make our code more readable and avoid repetition, let's do just that. Let's bind the discriminant to a name. To bind values in Scheme, you use a let statement. And it turns out the plugin I'm using has some templating in it. So I was able to just type let and tab, and it filled in the parens and stuff for me. If you don't have the same plugin, when you set up the let function like I did before, it's helpful to have the opening and closing parentheses written right at the beginning. So as the template is hinting here, the first parameter to the let statement is a list, and that list is the list of bindings. You can see that it's using the term variables. I'm trying to be a little more particular and I'm avoiding the term variables, but you get the idea. Now, each element of this variables list, as it's labeled here on the screen, is actually a list itself. Each of these member lists has exactly two elements, the name and the value that's being bound to that name. So I'm going to create the value DISC for discriminant, and then I'm going to write the code that's going to calculate that value. Okay, and we always want to do a sanity check that we have some balanced parens. The syntax highlighting helps a lot here. So we can see, for example, we've got the b squared right here outlined in the blue parens, and then the other part of the discriminant, the minus 4ac. And then the orange paren is the end of that name value pair that we've just created. And then the blue is the end of the list of variables we're creating, or bindings we're creating. You'll see that there's a double set of parens. Notice we got the blue paren and the orange paren right next to each other. And that looks a little weird, but realize what you have is the blue parens delineate a list. That's our list of name value bindings. And this list has exactly one element in it, and that is the discriminant name value pair, which is itself a list delineated by the orange parens. Now I'm actually going to tweak this a bit. I'm going to tweak it a bit to line up with the example that's in the textbook. And so what the textbook does is they implement the quadratic formula this way. They've broken it into a left half and a right half, where the right half is what's both added and subtracted. So I'm going to make that change here. And the other benefit of that change is we're going to have two name bindings, not just one. So here, instead of just having the discriminant, I'm going to change the name to right side. And I'm going to take that discriminant and divide it by the denominator. All right, now let's check our parens. Notice here we're ending with a purplish one, which closes out the expression, the square root of the discriminant over 2a, but it doesn't finish off the name value pair, so I am missing a paren there. I also don't have a matching paren for the list of variables, so I'll put that in. But what I want now is a second variable, so I'm going to bring this paren down so that what we have is one name value pair per line. And so the left side is just going to be negative b over 2a. Again, here notice that the parens line up. We can see that with colors. We can see that with the gentle highlighting here. Okay, so now that we have right side and left side defined, we can use them to calculate our roots. Now in Scheme, when you define a name value binding like this, you can only use those names within the let statement itself. The reason is so that these names that you create don't conflict with names you may have created elsewhere, like in other functions. This gets at the idea of scope and namespaces, both of which we'll talk about fairly soon. But for right now, just realize that these new names we create are only usable inside that let statement. And that would be what these empty parens are for here at the bottom, and that is the code that's going to use the name value pairs. So what we want the return value of this let statement to be is a list itself. Remember, quadratic equations have two roots. So we have a list here, that empty set of parens. And so the first element is where we add the two sides. And the other element of that list is where we subtract them. Now I like to organize this a little bit differently. I'm going to put the closing paren for the let statement on its own line. You're welcome to use any reasonable style you like. Now, this is almost what we need. There's a subtle bug in here that I put in on purpose. Take a minute and see if you can find it. And this isn't like a typo or something. I've forgotten something. All right, so let's try to run this and see what happens. So I'll create a terminal. Don't need the debug console right now. Oh yeah, I forgot one thing. I gotta run the function. So I'll do quad root. We need some parameters. So how about if we go with x squared minus x minus 6. And then I can say kava quadratic SCM, and let's see what happens. Okay, it does complain. And so what we can see from this complaining is that the problem is at character 32 of line 4. So there's a bug in here, and that's not where I meant to put the bug. So maybe that's the bug you saw, maybe not. Do you see a bug on this line? It's actually this right here, 2a. We need some operators in there. Lovely. If I hadn't made that mistake so long ago, I just would reshoot and edit it out, but I'm being lazy, so I'm going to use this as a teachable moment. Right, dirty secrets of lazy professors. All right, now let's see what happens. Okay, so there still is another bug. Look at it again and see if you can find it, assuming it's not the one you found the first time. Again, this is intended to be a little more subtle. So let me show you something like if this were to happen to you, how would you go about finding where the bug is? Now we saw one example a minute ago where right at the top of the stack trace, notice this is a Java stack trace because Kava is implemented in Java, it pointed right at the line and said, right here is the line where your bug is. In your source code on line 4, you have a bug. It wasn't quite so nice here. And unfortunately, the error reporting can at times be a little bit confusing. So let's see what we can discern from what it does tell us. It says argument number 1 has the wrong type. It expected a procedure, sequence, or other operator. It's expecting an operator, but what it got was, I think this is referring to a floating point number. Now, if we look down, what you'll see here are refer to lines of Java code. So these are lines that are passing up an exception in the JVM itself. So that's not really helpful unless you want to dig out the Kava source code. So what you do is you look down and you look past all of that Java stuff to the first line that's actually referencing your source code. So if we dig down a little bit, what you see is our problem is on line 6. You see anything? So remember, what we want here is we want to create a list. We want a list of two numbers, the root you calculate by adding the right side and the root you calculate by subtracting the right side. And that looks like what we have here, right? The blue parens are forming a list and there's two elements on the list. But remember, in almost all cases, when Scheme sees a list, it's assuming the first parameter of the list is a function to be executed. And that's what it's complaining about here. It's going to calculate one of the roots of this quadratic equation, which is going to come back as a number. So let's say that number is, for example, 2. So then it's going to try to take 2 and execute that as a function. Well, it's not a function, it's just a number. And so that's what the complaint is right here. It's trying to treat this list as a function call, but the first thing in the list is not a function that can be called. So here's how you fix that. There is a function in Scheme called list. And what that function does is it makes a list out of the following parameters. So this should fix that problem. Rather than trying to execute a number as a function, it's going to execute the function named list and build the list we want. Let's see what happens. No errors. That's nice. But I didn't tell it to print anything. Unlike the interactive program, it's not going to automatically print something every time you execute a command. We need to tell it to print. And in Kava, the function that sends something to the screen is called display. I'm going to do this the quick and dirty way and just display the return value of that function. And it tells us that the roots of this equation are 3 and -2, which is in fact the case. Now this is a little bit ugly down here because there is no return at the end of that output. So the output of the program runs right into my command prompt. So let's clean that up just a little bit. So what we want is to display the output followed by a new line. And here's how I'm going to do it. I'm going to use a formatted display. So what I want is some value. So this is going to be kind of like printf. So in C, you would do a %d or a %s or something like that. In Kava, we can do a %a. That's our placeholder. And then I want a new line. So that's my format. And the parameters to the format are the things that will fill in those placeholders. Need one more paren. Does that look nicer? There we go. So again, just to be clear, the format works a lot like a printf, right? Format is kind of like printf. You have your format string where you type out whatever it is you want to appear, but where you have variables you want to insert. Instead of a % something or other, like with C, you'll use a tilde-a. And that tilde-a can be anything. I don't think it literally stands for anything, but if that helps you remember it, go with it. So with the tilde-a, you can put numbers, you can put other strings, lists, whatever makes sense. Let me make sure one thing's clear. Notice that the call to format is nested inside of the call to display. These two functions together act like printf. The format function does the formatting. It generates and returns a formatted string. That return value then becomes a parameter to display, and the only thing display does is take a string and put it on the standard out so you can see it. The separation of behavior between display and format is a quirk of Kava. Other implementations of Scheme let you do the formatting right inside of the display function itself, and you don't have to use a separate format function. So that's more than enough new stuff for one video. In the next video, we'll look at conditional statements.